Isn't that a fancy little trick, huh? That's not so bad. Now, we can do the same thing with all kinds of nasty functions. Like, let's say that I have sine squared of x cos cubed of x dx. Now, watch this guy. So look close. Well, I know that sine is the derivative of cosine, or close to it, and I know that cosine is the derivative of sine. So what I really got to ask myself here is, what do I want to do? Problem is, if I just launch into this and I'm all, okay, I like things to be positive, so I'm going to let u equal sine x. Okay, that's cool, except the problem is, when I let du equal cos x dx, notice this is a cos cubed x. So I got to do something with the other cos squared x. Hopefully the spidey sense is tingling, and you're already seeing that this can be rewritten as sine squared x times 1 minus sine squared x, right, times cos x dx. And now look at how pretty that is. I need a cos x dx. U is sine, so wherever I see a sine, stick a u. This is the integral of u squared times 1 minus u squared times du, because that's what cos x dx is. This is the integral of u squared minus u to the fourth du. That's easy as falling in love, isn't it? U cubed thirds minus u to the fifth fifths plus c, and I'm done. I can walk, crud. No, I have to back substitute because I started out with a function of x. So I end up with sine cubed x thirds minus sine to the fifth x fifths plus c, and I rule. Now, that's simple. Those are trigonometric integrals. Now what I'm going to do is I'm going to do something called a trig sub. It's a trig substitution, and it's a little crazy. I'm not expecting you to get this straight out of the bat. We spend a lot the textbook has like 4 pages in this section, right? And I think I spend 2 or 3 days in this every single time because they are tricky. I'm going to start with the easiest trig substitution that you can think of. Now, notice, if I take the integral of the square root of, let's say, 4 minus x squared dx. Now, this would be a really easy problem if I had definite integrals on this, because I know that if y equals the square root of 4 minus x squared, then think about what this would imply. If I do a little bit of algebra, I know y squared equals 4 minus x squared, so x squared plus y squared equals 4. But Ridley, that's a circle. You're absolutely correct. What we're really doing is we're taking the integral of the top half of a circle of radius 2. Problem is, this is an indefinite integral. So I'm going to do a trick, and it's a trig substitution. And if you've never done these before, they're really hard to see initially, and I do something that's really crazy, but I want to show you how this is done. Watch. I notice that this is the square root of 4 minus x squared. Do you guys realize that if I could somehow turn x squared into a 4, I don't know, let's say sine squared x. If I could turn x squared into 4 sine squared x, then wouldn't that imply that I would have the square root of 4 minus 4 sine squared x, which is equal to 2 times the square root of 1 minus sine squared x. 1 minus sine squared x is cos squared, so this would turn into 2 cos x. Now you may right now be going, Ripley, what the heck are you doing? Well, I've created sort of a logical fallacy right here. I'll show you. I can't let x squared equal 4 sine squared x, but what I can do is, now let me change colors just to get us where we need to be. I'm going to take the integral of the square root of 4 minus x squared dx, and I'm going to let x equal 2 sine of theta. Now, I have committed no fallacy. Remember, I can substitute in integrals. I can substitute whatever I want, wherever I want, as long as I account for all of the integrand. So far, I have accounted for the x's. 4 doesn't scare me. It's a constant. All right. However, I do need to account for this dx. So dx equals what? Well, it's 2 cosine of theta, and then what goes on in the end? I just differentiated theta as though it was an x, so I have to leave a little footnote. It's like an implicit differentiation. Okay? Now watch what happens here. That implies that this integral becomes the square root of 4 minus 4 sine squared theta, right, times 2 cosine of theta d theta. Now I'm going to use this little chunk right here that I did before, and now watch what happens. We know this guy turns into this guy. So what I end up with is the integral of 2 cosine of theta times 2 cosine of theta d theta. So this whole thing turns into 4 times the integral of cosine squared theta d theta, right? Now, this is where you don't want your own trig to trip you up. You might say, well, cosine squared, that's 1 minus sine squared. That's easy. Well, yeah, except you're still taking an integral of something that's no kind of fun. The cos squared term is what's nasty. This is where we want to use that one powerful identity. I go 4 times the integral of 1 plus cosine of 2 theta all over 2 d theta. Let's suck that 1/2 out, and I end up with 2 times the integral of 1 plus cosine of 2 theta d theta. All right? These are kind of like the Energizer bunnies of integrals. They really do keep coming at you. Now watch. This becomes 2 times, you ready? Theta plus sine. Let's see, the antiderivative of cosine is sine, right? So the antiderivative of cos 2 theta is sine 2 theta halves, right? Nothing to it. And then, of course, plus c. So this guy ends up, if I distribute through, becomes 2 theta plus sine of 2 theta plus c. All right? Now, I'm going to show you a trick, because now we're in a bit of trouble here. Now we've got these thetas, right? And remember, we started this thing out with x's. But watch what I do here. I think you'll like this. This is clever. I'm going to turn to a red pen so we can look. Do you all agree that if x equals 2 sine theta, doesn't that imply that the sine of theta equals x halves? Doesn't that imply that if I have a right triangle with angle theta here, the sine of theta, which is opposite over hypotenuse, is that guy, right? Does that make sense? And then this guy right here is going to be the square root of 4 minus x squared. I might need that down the road, okay? Does that make sense? All right, so let's just have that sitting there for us for just a sec. Excuse me. So I need this whole thing in terms of x, right? So I'm going to do some voodoo here, and it might freak you out at first. The first thing that I'm going to do is, if I need just theta, if I come back up here, you know what, I need to change colors again. Do you all agree that theta equals the inverse sine of x halves? That's free of charge. I know that theta equals that. So you might come down here and say, okay, well, theta equals, so this is going to be 2 times the inverse sine of x halves, right? Now the question becomes, how do we deal with this and make it pretty? Because I suppose we could write plus sine of 2 times the inverse sine of x halves if we wanted to. But you see how ugly this is? And I really do have to deal with this sine of inverse sine garbage that we have going here. So what I'm going to do is I'm going to change colors one more time, and then I'm going to do something tricky. There's nothing I can do about this theta. This theta is along for the ride. It is 2 times the inverse sine. I guess that it's not 2 times it, it's the inverse sine of x halves. But watch. Do you agree that the sine of 2 theta, hopefully you remember from back in the day, sine of 2 theta, from that half angle rule, I can write this as 2 sine of theta times cosine of theta. Let's not forget our plus c. Now watch. This is the fun part. This becomes 2 times the inverse sine of x halves plus, well, I know that 2 sine theta from my original substitution is x. That's a freebie. Cos theta. What is cos theta? Well, cos theta is, you see what it is? It's adjacent over hypotenuse. So it's going to be x times the square root of 4 minus x squared all over 2. And you guys thought that trigonometry was dead and gone. Now, I realize this is a lot to absorb. And I promise you that we're going to do a bunch more of these in class, okay? I'm not going to leave you hanging with just this one little episode. However, I do want you to notice, look how cool this is. I mean, I just came up with a solution to this indefinite interval. As long as I'm between the values of -2 and 2, I can plug this in and find the area of any portion of the circle of radius 2 if I go from anywhere to anywhere. Right? I can go from -1 to 1. I can go from here to here. Find that area right there. All I need to do is plug it in. It's pretty cool. All right, right on. Enjoy. We're going to go on and do integration by parts here. Did I say parts? Sorry. Integration with partial fractions here in just a sec. So thanks for your time. See you in a sec.